All right, we're good. We're live. Yay, Sisu, baby. Okay, so let's say we have a function that looks like that, right? And we have this x value here that we're going to call x or x equals c. You know, x or x equals c.
When you wrap things up, I have a question. Do you mind? I have a computer question.
Oh, sure. Yeah, I had to restart mine just now because it was messing up. But,
Just whenever you have a chance.
okay. All right. I should go over there now. Okay. So we have a curve. Let's call it f of x. And we have a point of interest, call it x or x equals c. All right. What we're doing here is we are using the tangent line to approximate a function value to the left or to the right of c. Now, typically we draw it to the right. So let me just draw this value here. Okay, and we'll bring this down. No, this is part of an example. I'm just trying to get y'all to understand what the differential is. I'm not going to even call it x equals c. I'm just going to call it x. Okay, so this distance here, the distance that we're projecting out, I'm going to call it delta x, right? We called it h back when we did the limit. Now for marginal, returns and stuff, for marginal profit, that's always equal to 1. Delta x is equal to 1. So this x value here is x plus delta x. All right. Now, of course, this value here is f of x. And this value here is f of x plus delta x. And this is really what we want. We want this value. But a lot of the times we can't find that value because we don't know what the curve is. We measure a rate of change at a moment. So what we do then is we use this value here to approximate it, right? So let's call this function L, and we'll call this point here, we'll call it L of x plus delta x. Now, here's where dx comes in. The slope of this tangent line, this is where I'm deviating a little bit from the diagram on the paper. Rise over run. Yeah. A line has a slope of rise over run. Now, because dy dx is equal to the slope of the tangent line, which I probably should have used purple there to color code it. I'm getting better. All right, there we go. We can call this dy, and we can call this dx, right? Rise over run. And therefore, we can actually let delta x, in this case, be the same as dx. They're one and the same, okay? But delta x is going out on the actual curve, and dx is going out on the tangent line. It's the y values that differ, okay? When you measure the actual change, okay, if I were to bring this value across here, this, of course, is f of x still, right? This value right here is delta y. That's the actual change in the function values, right? If I were able to calculate f of x plus delta x, let's say it was 7, and f of x where I centered my approximation was 5, then the difference would be 7 minus 5 or 2, right? I would have gone up 2 units in actuality. So a lot of times we can't find delta y because we don't know the equation for f of x past there. But this, let me go back to purple, this distance is dy. See that? That's the change in the y value of the tangent line. Because the tangent line, L of x equals f of x, right? F of x at that point equals L of x. They share the y value there, they share the slope. So dy is the change in the tangent line, and delta y is the actual change in the function value. So that's what the differential of y is. You can think of dy and dx then as individual quantities. And then, so here's the idea. The idea is this: linearization or Taylor polynomials in general is this idea, okay? For small delta x, comma, dy approximates delta y, okay? That's the whole idea in polynomial approximation, not just lines, but later on when we study quadratics and cubics that represent functions. If we can stay within some vicinity, left or right, called a radius, of the center of the approximation, the tangent line or the polynomial in general becomes a decent approximation of the actual curve. Is it going to be exact? No. The closer we are to the center, the better it is, because this piece right here, if you want to look at it, that's of course the error, right? And you could see that if we go out further, it's getting bigger as we go to the right. Now this curve is concave down, much like the one we did yesterday with the cube root of x, but these are separating a lot faster than the other ones, okay? So that's the idea. So if you're ever just talking about the differential of y, that's what it is. It's the change in the y value from the center of approximation to how far out we're going. So when we get into integrals, here's what we could do. We can say that the derivative of y with respect to x is of course f prime of x. But what we can do, since these are individual quantities, is we can actually multiply both sides by dx, and this becomes the differential of y is equal to f prime of x times the differential of x. And what this does is it separates the variables, okay? So we get y values on the left and x values on the right, okay? So that's the derivative in differential form. And there's applications of that. If you want to read down below, you know, here's a nice application. You could think of dx as the tolerance, okay? I'm not going to do that example, but I will tell you this. Where did I go? Oh, once we separate the variables, here's what we're going to be doing. We're going to be soon studying antiderivatives, going backwards, undoing derivatives, okay? And there's a symbol for that. It is this symbol right here. It is the integral symbol. So if I can separate the variables in a function, I can do what's called integrate both sides. If I do it to the left side, I'm going to do it to the right, and it looks like a super S. We'll talk about why in chapter 4. But now we're taking the integral of 1 with respect to y, and then we're going to take the integral of this function with respect to x. Okay? It's called integration. Yeah. But integration is just really the same as anti-differentiation. They're interchangeable. Okay. So I could take the derivative in differential form. I might want to do that. Let's just do that one example. Let's do example 5. What this is called is differential form. So find the derivative of each function in differential form. So look how easy it is. I'm going to take the derivative of y with respect to t. That's what I would normally write, yeah? And it's going to be 6t squared plus 10t minus 3. There you go. But if I want it in differential form, I multiply both sides by the independent variables differential. So now it would be the quantity 6t squared plus 10t minus 3 times dt. That's just differential form. Okay. Now, if you know differential form is what you want, you can go straight to that step. You can say dy equals the derivative in parentheses dt.
Because it's just like you're multiplying it from this side to different separate.
Yeah. Now there's a couple of reasons why I want to do it, Mason. Like I said in chapter 4, if I wanted to go backwards, I need to be able to separate. I have to take the derivative with respect to a single variable. I have to take the antiderivative with respect to a single variable. So once I separate them, this is like an imaginary one in here. These become like bookends. I have the integral with respect to y, and I have the integral with respect to t, okay? And that'll make more sense later on, but we have to be able to separate the variables. The other reason is this right here. I said it wasn't going to work it, but it's nice to know. Here's a nice application of differentials, okay? If delta x is small, again, we could say dy approximates delta x. In this new context, though, we can work cooler types of problems like the following. Let's look at it. A machine's spherical bearing was measured with a caliper, okay? You just open it, you stick the bearing in there, and you can open and close it, and it gives you exactly what the diameter is, okay? So this would be like in a manufacturing plant. They want their product to come out the same every time. Now, there is natural variation from one production unit to another, and so they set up these tolerances, right? Quality control. If it's outside a certain tolerance, it's no good, right? But if it falls within a certain allowable variation, they'll take it, okay? The bearing's radius was found to be 2.3 inches with a possible error no greater than 0.0001 inches, okay? If a bearing then that's 2.3 inches can vary as much as 0.0001 inches, that could be smaller or bigger than 2.3, then what's the maximal possible error in the volume, okay? So here's what we're going to do. Let's go ahead. Here's a sphere. Here's the three-dimensional depiction. It's a pink bearing. Here's the radius r. Okay. We're going to be using spheres quite a bit. The volume of a sphere, if you don't know it, is 4/3 pi r cubed. You might want to commit that to memory. The volume of a sphere is 4/3 pi r cubed. Ethan already has it. Look, he's looking up. That means he has it, right? Watch this. What's the volume of a sphere?
4/3 pi r cubed.
See, he knows it. He knows it. Pomegranates are good for the brain. All right. So this 0.001 inches is the variation on the radius. So this is going to be, oh, did I? Crap. Yeah, I do that a lot. There we go. That's going to be your differential of r. That's the differential of the radius. We want to figure out the maximum possible error in the volume. So we're looking for the differential of the volume. That's what we want. Okay. When r equals 2.3. So here's what we're going to do. Let's go ahead and take the derivative of the volume with respect to r, but we'll do it in differential form. So here we go. The derivative of v with respect to r, which I don't write, is equal to multiply and subtract. We get 4 pi r squared times the differential of r. Okay. And again, you could do that in a two-step process. Take the derivative, then multiply both sides by the differential of the independent variable. And now we can plug in when r equals 2.3 colon, right? We always show what we're doing. The differential of the volume is 4 pi times 2.3 squared times 0.0001. And let's see. If y'all are curious what that is, I got my handy dandy calculator right here. 4 pi, unless you can do it faster than I, 2.3 squared times 0.1230 Okay, we get the differential of the volume to be 0.00664766101 cubic inches. Okay. So what is the meaning of that? Yeah, the volume will differ by no greater than that. So if we're machining these ball bearings and 2.3 inches is our desired radius, okay, or 4.6 the desired diameter. According to whatever we're going to be using these for, they can differ by up to 1/10,000th of an inch. They can vary by that much, bigger or smaller. If they're outside that tolerance, we can't use them, okay? But that means that when we take the volumes, the volume of those spheres are going to vary by no more than this 0.00647. So that's what that means. Okay, so it's a nice application. Yeah,
That's in both directions, bigger and smaller.
bigger and smaller in both directions. Yeah, it's a radius. It can go left or right. Yeah. Oh, yes. Yeah. You would definitely. Now, in this case, when we go 3 decimals on DR, obviously we don't want to do that, right? 0.000. So it would specify, or they would give you different numbers so that if you truncated, you could still do 3 decimals. Yeah, good question. I just wrote them all out here. All right. It sometimes might specify, list your answer to 4 or 5 decimal places. If it does, you go ahead and do that. If not, 3 decimals, round or truncate. Okay, so that's what a differential is. And again, we're using that to predict, right? We're using it to predict out a certain amount. And we know that the actual, here's the actual, right? But here's what we found. And then we know that that's an upper bound on the error. Okay, kind of an upper bound on the error. Okay, so there's linearization. Basically, find the equation of a tangent line, call it Gym of X, call it L of X, and then plug in an X value. Use your squiggles, right? The actual is approximated by Gym of X or Gym of 5, whatever, L of 5, which is this with units. And then if it asks, don't volunteer it if it doesn't ask. Is it an over or under approximation? If you know the curvature, cite it. If not, find the second derivative and look to see what the sign is on the interval between the center and your X value that you're using, okay? And put the smaller one first. Usually it's the center because usually we're predicting to the right, but we don't have to, okay? And that's it. That's linearization. That's the whole lesson. That's a nice application of derivatives.